Hello, so today we are going to talk about the Fibonacci series and how we can use linear algebra to get the subsequent numbers in a Fibonacci series, and how we can use the Binet formula, how it works in Fibonacci series, and how do we derive it using linear algebra, and see the extension of Fibonacci series from natural numbers or whole numbers to real and complex numbers as well. So first of all, Fibonacci through linear algebra, there are different ways you could go for, and there's a general basic formula that you might know of, but again, it's helpful in different ways. And again, deriving the Binet formula using linear algebra is a choice, and it depends upon your need rather than it being the easiest method to go about it. Now, before I actually get into things, I just want to give a clarification on what exactly Fibonacci series is, or recap or something. So you see, this is the first term, and this is the second one. So when I add these two together, I get the third term. See, 1 plus 1, 2. And then when I add the second term to the third term, I get the fourth term. This is 1 plus 2 giving 3. And similarly, this term to this one to give this one, and so on. So you have 1 plus 1 giving 2, and 2 plus 3 giving 5, and 5 plus 8 giving 13, and 21, 34, and it keeps going. So now, before we get into the crux of it, let's just see what the topics are. So there's Fibonacci series and basic linear algebra. Then we are going to see negatives in Fibonacci series. We're going to get into the Binet formula to linear algebra. We're going to derive it basically, and this is going to be really a large part of the video. And lastly, we're going to see a little bit of complex numbers in the whole Fibonacci idea. Now, first of all, we are going to derive, as I would like to call it, a Fibonacci matrix. So let's see. Now, F is the Fibonacci matrix that's denoted by that, and I would multiply it to these terms. So this is the n minus 1th term and n minus 2th terms. This could be 1 and 1, this could be 2 and 1, this could be 3 and 2. You get the point that this is the certain term of Fibonacci, which is after this term. Yeah, and clearly, this comes here and this comes over here. The sum of the subsequent terms is going to give the next term, the nth term, which basically is going to be like this. And this one's going to come to the bottom because this is the term before this particular term in the series goes on. Now, if you were to notice over here that the fn minus 1th term has a coefficient of 1, the fn minus 2th term has a coefficient of 1, and this as well has a coefficient of 1. There could have been a fn minus 2th term which is not there, so it could have a coefficient of 0 multiplied with fn minus 2th term. Oh, the handwriting is pretty lousy, just ignore that, yeah. Anyways, so you see, this is the coefficient of 1 over here, coefficient of n minus 2 over here, and coefficient of n minus 1 again, and 0 from the n minus 2. So I would like to call this a Fibonacci matrix. And now you see, that's where the magic happens. So you see, whenever I multiply, these are two Fibonacci numbers, and I multiply it with this, I get the next Fibonacci number. So if you see here, a bunch of Fibonacci matrices, and this is the first and second term of the Fibonacci matrix, and I multiply them and I get 2 and 1. Oh, great. Now, if I multiply these two together, I get 3 and 2, which again, if you look over here and compare it with this, yeah, it works. Again, 5 and 3. The next one, 2 plus 3 giving 5, and the 3 coming to the bottom, and so on. Now you'd be like, okay, you're just adding that stuff. I don't see why that's a big deal, and you will see why we actually need to derive such a, or come up with such a mechanism to go with it. But before that, let's look into the negative Fibonacci numbers. So oftentimes when we think of this whole series, we actually ponder upon this part of the whole system, because oh yeah, these are the positives and these add together. But if we actually go back in the line, it does work. So you see, minus 1 plus 1 actually gives 0, 2 and minus 1 give 1, and so on. So it can be seen that it actually follows up this formula where every alternate digit is negative, and it works out. So now comes here the formula that's going to take up a good lot of footage in the video, the Binet formula. So the n over here is the term that we're talking about. So let's say I'm talking about the first term, then I'm going to put n equal to 1. I'm talking about the whatever term, second term, I'm going to put again 1. If I'm talking about the 0th term, I could put in 0. If I'm talking about negative 4th term, I could take this term, so I would put in 4 and I would get minus 3. So now you might be like, what the hell is this particular thing? What the hell is this phi? It's the golden ratio, which has the value of 1.6 something. And this is actually something like 1 plus root phi by 2. You must have heard this about this quantity. You must be recalling that, hey, this is something that comes up. But yeah, let's see how we derive it, and at the end of it, it must be clear on what exactly we are doing here. Now, so for the system that we were looking at, you have a u0 into u0 equal to u1. So you see you have something over here which is being multiplied with another something, which is, I would say, the 0th term, giving the next term, which is u1th term. Now, the general form of dynamic sequence modeled here has A as the transformation matrix, u0 as the initial state, and u as the final state. Now, from the general understanding of linear algebra, I could say that, hey, A is equal to S into lambda into S inverse. Yep. So this lambda over here is a 2 cross 2 matrix with eigenvalue of A at diagonals and 0 elsewhere. And okay, and I need to break it into this form. So we'll plug u0 and u1 from this one into this, and it'll get something like this. Now, as we can see, this is something that's working for first term, and this is the 0th term. But what if I have to take something really large, like I have 100 terms or 200 terms, and to go bigger? So I could move to k terms, and my equation would look something like this. Now, in general, if I were to solve it, I would have to multiply like what, 100 or 200 or 300 matrices. But luckily, with the usage of linear algebra, or in this particular case, since it's a 2 cross 2 matrix, I don't have to do so much. I can use the idea of eigenvalues and eigenvectors. So you have here the determinant of this particular quantity, lambda I minus a equal to 0. Or I could say that the roots of this particular equation is going to give me the eigenvalues. So you remember the Fibonacci matrix that we derived? I'm just applying this over here. I'm subtracting a lambda I from it. So you have the Fibonacci matrix, Fibonacci matrix, Fibonacci matrix, and a 0 over here, from which I am subtracting the minus lambda multiplied with the identity matrix. So you get something like this, and you get a characteristic polynomial. So moving on, we'll have to solve this characteristic polynomial, and we get two values of lambda. Lambda 1 is 1 plus root 5 by 2, and lambda 2 is 1 minus root 5 by 2. And now I can substitute it back from the previous equation. So we have this, and I'm going to put in the values, plug in the values of lambda, and I get something like this. Now, first of all, I'm going to consider lambda 1, and then move to lambda 2 as time comes. So I get an equation like this. Well, if you were to notice that x2 is independent or free variable, and I can give it any value I like in it for universe. And I choose to give it the value of 1 because it's going to be easier for calculation purposes. So by writing 1 here, I get x1, I multiply root 5 plus 1 and divide it by again, so that it doesn't make any change, and it goes to root 5 plus 1 back 2. Now I do this again with the other vector after I get the eigenvector for lambda 1. I do it for lambda 2. Now recall that lambda 1 and lambda 2 are going to be orthogonal because my overall matrix is symmetric. Next, we need to find its adjoint and divide it by its determinant. Now clearly this is a 2 by 2 matrix, and one trick that you can apply here, because it's 2 by 2 matrix, and we can have an easier life by doing this. So you just switch these two. So like I swap them, and the D comes here and A comes here, and then I change the sign of these, and this becomes the adjoint of the initial matrix, and this goes in for the 2 cross 2 matrix, but yeah, and then divide it by determinant. So once I'm done with that, I get the S inverse as well. Now going back to the initial thing where I had U0, and I'm going to multiply the S with C. Why C? And C is a 2 cross 1 matrix, because I have S as 2 cross 2, but I need U0 to be 2 cross 1, for which I need to multiply it with a C matrix. Once that's done, I get okay, so now I need to get the C, right? So in order to get the C, I have U0, the S coming to the other side, giving you C equal to C inverse U0. U0 now can be anything you want, so not exactly anything you want, but it can be any value of the Fibonacci series. It could be 0 and 1, it could be 1 and 1, it could be 2 and 1, because these all fall into the whole series. Now, since I'm using 1 and 1, the next term which I would get out of it would be the second and the third term. If I had taken 0 and 1, it would have been first and second term, and so on. But you could just make it work according to your requirement. So C is this, and I'm just going to plug in the values of C inverse and U naught, and I get something like this. So now repeating the process for K terms, since now it's going to be the part of K, and we have the C as well, so U will be equal to C divided by K into C. And so you just put in the values again, and you get something like this. Now if it were for only zero, starting from zero term, you would have to only consider this part of the equation, and it would go to something like this. Now I want you to, now you're like, oh my god, how did it switch from something like root 5 plus 1 to, yeah, this. So this thing over here is root 5 plus 1 by 2. Just again ignore the loss in gradient. Yeah, and this would be its inverse. So if you go back to this, look at this, then it's clearly this part. This becomes the shy 5, whatever. And yeah, this is Binet's formula. Now in this formula, when I was putting in positive ends, okay, I'm putting 1, 2, and I get 1 and 2 and all those numbers. When I put in 0, I get a 0 term. When I put -1, I get a -1 term. But what if I decide to put in, well, let's say fractionals? And if I put in fractions, I would see that, oh, this term over here is actually negative, because it's going to be 1 minus root 5 by 2, which is negative, and that cannot exist unless I were to think of complex numbers. So thinking of complex numbers, let's see. So you see this is the inverse of this particular quantity, and it's going to be negative. And if I were to plot this on a graph, it would come up something like this. So this spirally thing over here is the real part, and this curve, which I'm pointing at, is the root, the one that comes from the complex part of the equation. And if you were to actually zoom out of the whole thing, you'd actually notice that you'll be able to see only the real part, and the complex part wouldn't be quite visible after a point of time, at least from the bird's eyes view. And if you see at 1, you see this knot-like thing. It's because 1 appears 2 times, as you remember, 0 and 1 and 1 and 2. Yeah. So at the end of it, we can see that these numbers, the complex numbers, again follow the same pathway that others did. Like the Fibonacci number of z plus 1 is equal to Fibonacci of z minus 1 plus Fibonacci of z, just as it worked for positives or volts or negatives and so on. And well, that brings us to the end of the video. Behind these things, before I say thank you, these things on the background are the botany of how in botany the Fibonacci series is seen, and how Lucas series and a bunch of other series are visible. So yeah, thank you.